Hello everyone, in this video we are going to be discussing geometry on a sphere, where we are going to compare Euclidean and spherical geometries. So in a previous extension video we had talked about Euclidean geometry. That's the geometry that we do and have been doing this year, and there are other non-Euclidean geometries. So there are some very similar rules, theorems, properties, but some are going to change a little bit, and we'll notice that with spherical geometry. So, in Euclidean geometry, a plane is a flat surface that extends without end in all directions, and a line in a plane is a set of points that extends without end in two directions. Geometry on a sphere is just a little bit different. In spherical geometry, a plane is a surface of a sphere, just the surface. A line is defined as a great circle, which is a circle on the sphere whose center is the center of the sphere. So you can see a couple of great circles drawn to the right here. Alright. So, in Euclidean geometry, we can see exactly, a line on a plane, and then we see the great circles in spherical geometry. Alright, some properties and postulates in Euclidean geometry are true in spherical geometry, others are not, or are true only under certain circumstances, so we might have to edit our statements a little bit. So, for example, in Euclidean geometry, if you flip all the way back to postulate 5, so this would be in chapter 1, this postulate is true, or it says that any 2 points, through any 2 points there exists exactly one line. So here I have my plane, here I have 2 points, and here I have my line. I can't draw another line through those 2 points, and if I were to draw another line through this 1 point, it wouldn't go through that second point. Alright, so that's what that postulate says. Now, what it would mean in spherical geometry, on a sphere, this postulate is only true for points that are not endpoints of a diameter. So kind of dissecting that, we can see this sphere over here to the right. If I were to, pick at random 2 points, here's this point and this point on the surface of the sphere, as you can see, there's actually 2, and then I could draw in another circle, another great circle over here. There are infinitely many great circles, or, kind of the translation from Euclidean here, lines that pass through those 2 points in spherical geometry. But if I were to pick 2 points that aren't on the end of a diameter, because here you can see those 2 points are on the end of a diameter, I can pick, this point, and then this point over here. There's only going to be one line that goes through that, one great circle that goes through that, as long as they are not endpoints on a diameter. So that's where, we have similar postulates, but there has to be a little bit of editing. Alright, so on a history note, spherical geometry is sometimes called Riemann geometry, after Bernard Riemann, who wrote his first description of it in 1854. So example 1, compare Euclidean and spherical geometry. Tell whether the following postulate in Euclidean geometry is also true in spherical geometry, and then draw a diagram to support your answer. So one, quick way to think about it, I'm not great at drawing spheres, but here is, one circle, and then in order to draw the depth, you kind of draw that arc like that, and then you draw a dotted arc to the back. Alright, that's how you draw a sphere. And in addition, one easy way to think about it is grab a soccer ball, a volleyball, a basketball, a baseball, it doesn't matter. Grab a sphere that you have in your house, your dog's chew toy for all it matters, and put a point. You can grab a piece of tape or a little sticky note, put a point there, and when we're talking about different things, think about it. Alright, with a physical model. So, parallel postulate. If there is a line L and a point A not on a line, so I've got a line, I've got a great circle, and a point not on that, then there's exactly one line through point A parallel to the given line. Now, if L here is my beautiful line, what we are calling great circles, there is definitely, I can pick this point A, there is definitely some sort of, circle that is parallel to it, but that is not a great circle. So I can create a whole bunch of options of great circles like we have in green, but this does not hold true. The parallel postulate is not true in spherical geometry. Distances. In Euclidean geometry, there is exactly one distance that can be measured between any 2 points. So between point A and point B, I have a straight segment and there's only one distance. Alright, if I were to take, a way around, that's not what qualifies as a distance. So on a sphere, there are two distances that can be measured between 2 points. Keep in mind we are working on the surface of a sphere. These distances are the lengths of the major and minor arcs of a great circle drawn through those points. So, looking at example 2, the diameter of a sphere is shown. The diameter of a sphere is shown as 15 units. And the measure of arc AB, remember, I flipped the page on us. Alright, the measure of arc AB, anytime they write it like that with 2 letters, that signifies to us that they are talking about the minor arc, is 60 degrees. So I can mark that as 60 degrees right there, 60. Find the distances between A and B. So when we are talking about arc length, they did say length, it's a little bit different than arc measure. Alright, so instead of in degrees, it will be in units. Alright, so way back when we had this proportion of arc length, any arc length over the entire circumference is equal to the measure of the angle, the interior angle, which is also the same as the measure of that minor arc, over 360 degrees. So piece over a whole equals piece over a whole. That is a proportion. Alright, so I fill in variables for what I do not have, and then I fill in the numbers for what I do have. So our 2r here, that is our diameter, so 15 goes in there, and then my minor arc, which is the same as my central angle, 60 degrees over 160, and then we solve with an exact manner, leaving it as 2.5 pi instead of rounding it. And then I do the exact same for the major arc. And what we do there is we're still labeling it as x, we still have 15 pi, however, the measure of the arc is a little bit different. We have 360 degrees minus that 60 degrees, alright, which gives us 12.5 pi. And another way to find it, if this is the measure of just this piece right here of the minor arc, and our entire circumference is 15 pi, we could take that 2.5 pi away from 15 pi to find that 12.5 pi for the major arc. Alright, that concludes this video and the year in lessons. So, If you guys have any questions, please feel free to reach out via email or contact me during office hours. I look forward to hearing from you guys and wish you the absolute best of summer.